Everyone, my name is Nick from Coffee Before Arch, and in this new series, we're going to be going through a primer on memory consistency and cache coherence by Soren, Hill, and Wood, some great people over at the University of Wisconsin-Madison. So, throughout this series, we're going to, introduce what is memory consistency, what is cache coherence, go through some examples, and, we're going to integrate some more hands-on type stuff in this as well, actually simulating how we actually simulate coherence protocols, in contemporary simulators like Gem 5. But, so in this first video, though, we're going to go through the introduction to the book and really kind of set the stage for, why do we care about memory consistency? Why do we care about cache coherence? What's the difference between memory consistency and cache coherence? And then, basically just preface the rest of the book. So, of course we have to kind of preface where did this problem come, or where did this come from, right? So where did memory consistency and cache coherence, what's the kind of the root cause or the reason why we have it today? So, most, if not pretty much all modern chips are going to be multi-core chips. I don't think really anybody makes a uniprocessor anymore, except for maybe some embedded devices that are low power. But for the most part, even even a cell phone will have a multi-core or a chip multiprocessor now. And a lot of times we're supporting shared memory and hardware. So so what do we mean by this? So shared memory processors, they can read and write a single shared address space. So, we'll have two different threads running and they can access the same data. So what are the things we look for in a new architecture? Well, of course, we want it to have high performance. That's generally a good goal. Low power is a concern, especially with the power wall and the end of kind of frequency scaling. We're very concerned with how do we continue to improve performance without, drastically increasing power. And then, of course, we care about, we don't want to make things too expensive. We don't want to have things that are too hard to manufacture or, the end user will not buy. But, these are all kind of, null points. We don't really care about any of things unless we can first provide correctness, right? So we need to make sure that an arbitrary program that we run will be correct before we can start caring about improving performance, improving power, improving cost. High performance, low power, and low cost, but an incorrect program, that's a fail result. So, at a kind of hand wave level, as it says here, we can show that, or we can kind of imagine, I can imagine a system where, shared memory just works, but we see that, the obvious is not what makes having shared memory and needing memory consistency and cache coherence. The obvious case isn't what makes this difficult. What makes this difficult is subtle corner cases. So it's more of a death by 1,000 cuts type situation. So this is something that can be incredibly complex to really understand, and we have to treat it very carefully. So we're going to break this into two issues, as was kind of implied by the title, which is consistency and coherence. So starting out, what is the job of memory consistency, which can go by a couple different names, but I'll generally refer to it as consistency. So, it's the job of consistency to define shared memory correctness. So these are basically just going to be, what are the rules that loads and stores, you can think of these as memory reads and writes, going to follow. And so how do they act upon memory? So a consistency definition, ideally, would be simple and easy to understand. But, defining what it means for shared memory to behave correctly is more subtle than defining the correct behavior of it, for example, a single-threaded processor core. And so, this is for, a fairly straightforward reason. So when we have a single processor core, if this can be an out-of-order core, at the end of the day, we'll have one thread, we'll have a single instruction stream, and our correct output will just be the end of execution, where all programs have completed, and to the programmer it seems like they've all completed in program order. So while they may execute out of order, they will retire or commit the instructions that is in order. So there is a single well-defined output state that we're looking for. But this really gets complicated when we get to having multiple cores and multiple threads. And the reason why is because no longer do we have a single correct output. We have potentially multiple correct outputs. And so what I mean by that is we could have two different threads running on different cores, and they could interleave in different ways as far as which instructions actually occur when, and there'll be oftentimes greater than a single correct way that these interleavings can happen, and there can be many incorrect interleavings of how these two instructions concurrently execute. And so this is one of the things that makes multi-cores very difficult, is this idea of having all these interleavings and having a set of correct cases and then another set of incorrect cases, instead of just a single target correct case to shoot for. So but of course we've got to master this, right? So if we want to implement things like shared memory, we have to understand this problem and see how we can find ways of actually implementing this in a reasonable manner without sacrificing too much on performance. So that's kind of the basics of memory consistency. But what about coherence? So unlike consistency, coherence, generally referred to as cache coherence, is something that's completely invisible to software. And it's not even required. And the reason why it's not required is because you can have a system that doesn't have any caches. If you don't have any caches, you of course don't need cache coherence. So what does it actually seek to do? It really seeks to make the caches of a shared memory system seem functionally invisible. So it's to give the illusion that we have an access coming from a core. It's going to go to memory. That access will be fast, but we want to make it seem from a correctness standpoint that there's no difference between accessing, that piece of data as if it was really close to the core into the L1 cache, or if it was all the way down in main memory. We want to, define some kind of mechanism that can provide that. So, like I said, we don't want, from a correctness point of view, we don't want any new functional behavior to be introduced by cache coherence, meaning that it should behave as if there are no caches in the system. But, of course, if you actually look at timing information, you can, of course, see that you're not going all the way out to main memory for every access. So we're talking mainly from a functionality point of view. So, the reason why we talk about these two things together, even though cache coherence is not required, is that cache coherence is really a tool to help provide consistency. So, while we can have a system without caches, that's typically not the case. Typically, we do have caches. So, we want to, as I kind of said at the beginning, we want to really understand at a basic level how consistency works and how coherence works and how they work together. So, what we'll end up doing is, in the later chapters of this, we'll define coherence using a single writer, multiple reader type scenario. And, we'll continue on and show strategies for implementing different types of coherence, and also bring up the fact that we can have multiple different kinds of memory consistency models, each of which have their own quirks and their own optimizations. So let's start out, though, by talking about memory consistency. So as we kind of said before, consistency models define correct shared memory behavior in terms of loads and stores. And this, like we kind of said, this doesn't have to reference anything about caches or coherence. This is purely about loads and stores. It doesn't say anything about caches. So so we'll understand this with a quick example. So say we've got a computer architecture class that's going to be in room 152. And then all of a sudden, for some reason, maybe that room gets booked, it's under construction, so it has to be moved to room 252. So maybe, an email gets sent to the site admin to update the online schedule that says, it originally says, oh, this class is going to be room 152, move it to room 252. So, what the site admin might do is he might send a text message to, all the students in the class and say, check the newly updated schedule. But, maybe the site admin's busy at that time. Maybe he gets a phone call at that exact moment after he sends that message. So he can't actually update the room number immediately. So, if you're a good student, maybe you see that message immediately and you go, I should really know what this new room number is. But because it hasn't been changed yet, that person might still see room 152. So even though, eventually the ordering that we're expecting would be, okay, here is we've got, the room change. We have to change the room number. Then we have to send a message to everybody. And then, everybody reads the message and looks at the site. We see that we can get some out of order stuff going on here that leads to, if this was a CPU, we'd consider this a correctness problem. Some people are reading the incorrect value. They're reading room 152 when they should be reading room 252. So, even though the registrar performed the writes in the correct order, so, they updated the room on their end to be 252, and they told the site admin to update the room to be 252. Whoever that diligent student is, they saw a different order. So they saw the message that the room was updated before they saw that the actual room number change. And so that's this incorrect ordering that memory consistency defines whether is correct or not. So again, that's this idea of loads and stores and their ordering. So, although this is kind of a contrived example, it can happen in shared memory hardware. It can happen in the write buffers. It can happen with prefetching. It can happen with multiple cache banks. So, we need to define shared memory correctness so that programmers know what to expect and implementers know the limits to what they can provide. So, the programmer needs to know, what's going to happen when I run my program, and the people that say write the low-level libraries that actually interact with the hardware, they definitely need to know what they can expect from the hardware. So shared memory correctness is specified, like we said, by the memory consistency model or memory model. And it's going to specify the allowed behavior of multi-threaded programs executing with shared memory. So, our main topic in this is not going to be, say, single-thread performance or something. It's going to be, scenarios where we have multiple actors, right? So we're going to have multiple threads going at the same time, sharing data potentially. So as we said, unlike single thread, we can have multiple correct behaviors are usually allowed. And so memory consistency models can be, pretty subtle here as to defining, maybe this reordering is allowed and it doesn't, lead to any incorrect behavior, but maybe some other reordering isn't allowed, and because that would lead to incorrect behavior. So we'll go ahead and introduce those in chapter 3, starting at the most conservative and the most intuitive of memory consistency models, which is sequential consistency. And we'll continue on with there and bring up other types of consistency models used in things like the x86 machines and SPARC ones, such as total store order, and how these tend to violate sequential consistency, and they are more relaxed memory models is normally what we say, because they allow for more types of reordering of, say, reads and writes with respect to each other. And then we'll kind of cap it off with the extreme when we talk about relaxed or weak memory consistency models, and showing kind of the reasoning behind them, and what these really entail, and why we would even want these things in the first place, as well as what these memory consistency models have to support in order to have any kind of programmability. So that's kind of the basics of memory consistency. We skipped over a lot here, but that's mainly because that's going to be covered in the actual chapters that talk about memory consistency. So let's talk about the other side of things, right? So the other side of the coin is going to be coherence. So we can have a coherence problem just like we can have a consistency problem in situations with multiple accessors. And when we have multiple copies of data or datum in multiple caches. So, and at least one access is a write. So typically when we're talking about, memory consistency and cache coherence, what we really care about is writes. If everybody is just reading read-only data, there's not really going to be any problems because nothing's being changed. The problem is when something is changed and other cores don't know about it yet. So, we'll go back to the simple example. Computer architecture class in room 152, and let's say that after the message gets sent out, the room's going to be updated. Some diligent student copies the data, directly into their notebook. So, as soon as the actual room gets updated, right? So, we're assuming that the room is in 152, and then they get the student gets the message that the room has been moved, and to check to see what the new room is. They check to see the new room, and they still see 152, and then after that, the room actually gets updated to 252. Well, now that copy that's in that student's notebook is incoherent in this situation. So that's what we really care about. What we care about is, somebody having a local copy that isn't valid or shouldn't be valid. So take the case where you have two threads on say two different cores. Both of them say read a variable A that's in memory. They both get the exact same value from that read. Now let's say that one of the threads writes to A, right? So they're going to write to A, and maybe that just gets stored in the cache, right? But the other thread still sees A as being the exact same value that it read. So there's a problem here, right? Because one thread has a view of memory that's different than another thread, right? And so that's this incoherent situation. So this access to stale data, so in the case of this variable A, or in the case of this notebook where the room is written down, this is prevented by the coherence protocol. So the coherence protocol really tries to pretend that there isn't a cache in the system. So it's exactly as if all the writes are going to memory, right? But while still trying to extract the performance we get about having caches, we need to just make sure that they are coherent. So we'll really go into this in chapter 6, where we'll talk about the big picture of cache coherence protocols, as well as talk about some interesting ones building up from the very simple protocols to the more common and ones that are used in commercial architectures such as Moesi, that has a number of different states. So when we talk about these coherent states, we're talking about for every single cache block inside of a cache, it has a coherent state. So for the case of Moesi, this stands for modified, owned, exclusive, shared, and invalid. And we'll go into this later, but just to kind of preface this, so modified will mean that this cache block can be written to by this thread or read by this thread, while something like shared says this isn't writable, but it is readable, and exclusive says that this isn't writable, it is readable, and it's the only copy in the system. And we'll see why we even want, say, an owned state or this exclusive state to begin with. And then invalid is basically how we protect from these incoherent situations. So when these situations arise, we have to mark those. Whenever we have, say, writes, we have to mark other copies of the data as invalid. And then we'll also talk about things known as transient states. So we could have, updates that happen while we're in the middle of changing states. And this is where a lot of the difficulty comes in with cache coherence protocols. It's handling all of these transient states. So, other threads, they're not dependent on, one particular thread. So they'll be continuing on, they'll be doing, say, more reads, maybe potentially writes. And, as a result, we have to handle what happens if we get a request coming in while, we're trying to do a request. All right. So then we'll actually talk about, in the later chapters of 7 and 8, we'll talk about, ways we can actually implement coherence protocols. So, one of the common ones that we'll cover is snooping cache coherence protocols, where we have what's known as a Snoopy bus. So, we won't go into this in detail here, but you can think of a Snoopy bus as basically having, whenever we make a request or we want to do something like a write, well, we have to, tell everybody about it. So we've got to broadcast that over the bus. But, as this kind of sounds, once we start scaling to say, 1024 cores, right? This broadcast is going to start getting really, really expensive, right? And a lot of times it's just useless, right? So if we only have sharing between maybe a couple cores, why do the other, 1,000 cores need to know about it? So we'll talk about more scalable designs, such as directory-based cache coherence protocols, and really why those are attractive when it comes to scaling. And then we'll also talk about, some actual case studies, such as SGI Origin 2000, AMD Hypertransport and Hypertransport Assist, as well as Intel QuickPath Interconnect. And then finally, what we'll kind of conclude on is, Chapter 9, where we'll discuss some, more advanced topics in cache coherence that relate to things like, what do we do about translation look-aside buffers? How do we handle, coherent direct memory access? So, what if we have another core trying to reach into or another node completely trying to reach into our memory using something like RDMA or InfiniBand, and then things like virtual caches as well. So, this, consistency and coherence quiz, this is basically what overall we should get out of this book, and we should be able to answer. And so it includes a number of, very common things that we'd want to know. So, we should be able to understand that, in a system that maintains sequential consistency, whether or not a core needs to issue coherence requests in program order. We should understand, the memory if the memory consistency model specifies legal orderings of coherence transactions. I'll give you a hint. We talked about the relation of memory consistency and cache coherence and whether or not one is required for the other. We'll also talk about, what happens in, total store order. So this is a memory consistency model used in a similar memory consistency model as to what's used in a lot of x86 processors like, Intel chips. And what that entails, whether or not, how you can translate, a high-level languages consistency model, and whether or not you can just completely ignore the architecture's memory consistency model. Some stuff about some coherence protocols, such as the MSI protocol. And the MSI protocol is something that we'll actually implement as an example during this series, as well as, talk about Snoopy cache coherence and what it actually requires and be able to answer all these questions. So, that's really going to do it for this episode. It's really just kind of a primer on, what is cache coherence? Why is it so important? Why is it so difficult? So, just to kind of motivate why we need to understand this more and more, this is something that is not actually verifiable, right? So in modern parts, because of how many buffers there are in the system, because of simply the size of the memory structures, it's impossible to fully validate a design and say there will not be any coherence bugs, especially when you have designs that are supposed to scale to hundreds and hundreds of processors, right? the search space is just really too large. So we really need to understand this really foundationally, so that while we may not be able to fully validate these designs, we really understand where problems arise and how we can really kind of plan to prevent them. But let's go ahead and do it for this episode of memory consistency and cache coherence. So feel free to check me out on github.com/coffeebeforearch, where I've got a whole bunch of series as well on C++ programming, Python programming, parallel programming in C++, GPU programming with CUDA, and a couple others, like where I do research topics. And the other kind of series also coming from the synthesis lectures on computer architecture on GPU, the fundamentals of GPU architecture. But that's going to go ahead and do it for this episode. I'm Nick from Coffee Before Arch, and I hope you have a nice day.